better just to pick some numbers on a table. And like tables work, I know what numbers I want to pick. I want to pick -8, -1, 0, 1, and 8. Because I know what numbers are going to give me a whole number. So I'm really just looking at the table, type it in the table, find the whole numbers. The cube roots of -8. The cube root of -8 is -2. What can we multiply by itself 3 times to get -8? And that number would be -2. -2 times -2 is 4. 4 times -2 is -8. -1, what is the cube root of -1? What can we multiply by itself 3 times to get -1? That number is -1. -1 times -1 is +1. Times -1 is -1. The cube root of 0 is 0. Cube root of 0 is 0. What can we multiply by itself 3 times and get 1? That number is 1. So 1, 1 would be a point on the graph. And what can we multiply by itself 3 times and get 8? That number would be 2. 2 times 2 times 2 is 8. So cube roots look a lot like square roots on the right side. So I'm going to graph the right side first. So ignore the points on the left. But if we graph this right side, the right side looks a lot like the square root. It looks like a parabola, turned sideways and half of it chopped off. That is what we graphed yesterday when we graphed square roots. It's a little bit flatter than a square root though, but not a whole lot. Looks very, very similar to a square root. But since we can take the cube root of a negative number, we're also going to have, it's not just going to stop at that point. In this case, 0, 0, it's actually going to continue to go to the left also, because we can take the cube root of negative numbers. So that left side is going to look like a square root function also. It's just going to the left. So we kind of like have a square root function on the right, square root function on the left, kind of. It's kind of what it looks like, a little bit flatter. And if the right side goes up, the left side goes down. If the right side goes down, the left side has to go up. The x and y intercepts for this function in particular is the origin. So it passes through the point 0, 0, 0, 0. The domain, how far left and right does this graph go? This graph goes left really, really far. It goes left really, really far. And it goes right really, really far. So the domain would be -infinity to infinity. Algebraically, what does that represent? We can plug any number we want to in for x, and we will never get a domain error. Any number we want. What about the range? It looks like the graph's kind of leveling off right here. It's not leveling off, it's just increasing really, really, really slowly. And this side looks like it's leveling off, but it's really not. It's just going down really, really slowly. So the range is going to be -infinity to infinity. And guess what? The domain and range is always going to be -infinity to infinity for any odd roots. We're only going to graph cube roots, but the domain and range for any odd root will be -infinity to infinity. The end behavior. Since the domain is -infinity to infinity, when we talk about the end behavior, we're going to do what we did before with quadratics and exponentials. As x goes to -infinity and as x goes to +infinity, because the domain is -infinity to infinity. We don't have like an asymptote that says, hey, can't go any further than that, or we don't get to like a point where we can't go any further left than that. So that's what our end behavior looks like. This top line is really just the left side. This bottom line is really just the right side. So the left side of the graph is going down to -infinity, and the right side of the graph is going up to +infinity. So that's the basic graph with no transformations. No transformations at all there. What happens when we start transforming this graph? What is our key point? And our key point is that point that's not affected by the stretch, shrink, or reflection. And it's going to be this point that started at the origin. So when I start moving things left, right, up, and down, that's the point we're gonna move, and that's the point that's gonna be on the graph, no matter what the stretch, no matter what the shrink, and no matter what the reflection is. That point 0, 0 is that key point that we're going to follow with the horizontal and vertical shifts. All right, we did those already. We got 1/2 times the cube root of x minus 4. What is the x minus 4 going to do to our graph? It's going to move it to the right 4, good. And what is the minus 1 going to do to our graph? It's going to move it down 1. So right 4, down 1. I guess I should have wrote those over there. But if we go right 4 and we go down 1, my key point is 4, -1. My key point would be 4, -1. That's going to be that point that was in the middle of the graph. Like we said, like, hey, half goes to the right, half goes to the left. This point now, right 4 and down 1, is going to kind of be that middle point.
Should we put that by 1/2 or now?
We will. We're about to talk about that in just a second. So that's just that key point. It doesn't matter if it shrinks, stretches, reflects. Doesn't matter what that shrink, stretch, reflect is. That point will be on the graph. Okay, the 1/2, yeah, the 1/2 matters, but the 1/2 does not affect that point. Now, what does the 1/2 do? The 1/2 is a shrink by a factor of 1/2. So how are we going to graph that? We're going to use this to graph that second point the same way we graphed the square root point. We said, hey, the shrink doesn't affect like that x value. It only affects the y value. So that next point is still going to be just 1 point to the right, but instead of going up 1, if there was no stretch or shrink, it would be right there. We're only going to go up 1/2 of a point. And then we can draw the right side, which still kind of looks like a parabola on the right side. You can't. I'm sorry. Yes, but since this is a cubed root or an odd root, we have to go both ways. It's going to go the opposite. So instead of going up 1/2, we're going to go down 1/2 on the other side. That is correct. They can't go, both sides can't go up. But I would always graph the right side because the right side is just like graphing the square roots that we did the other day. The left side goes that way. That would be really cool if you could zoom in though, huh? Yeah. Or if you had like a tablet where like I could take notes on the board and you could write the notes on your tablet and it would automatically save it in your Microsoft Teams account. Because I could do that. Like that's possible. I could push this entire notebook into your Microsoft Teams account where I write on them. I could push a blank copy to you that you could write on and it would automatically save it. And then we could be like a completely like paperless classroom.
But you also got the school's internet would be a big problem.
It would be because everybody would be on the internet at that point. All right, the domain and range. The domain and range, negative infinity to positive infinity for both. Does not matter what the transformations have occurred. If it is an odd root, that's going to be our domain and range every single time. The end behavior. The only thing that's really going to change on the end behavior for these is that second number. And that really just depends on whether it's been reflected or not. So in this case, it has not been reflected. So the left side is still going down and the right side goes up. So the left side end behavior is negative infinity and the right side end behavior is positive infinity. Cool. All right, last one for today. X and Y intercepts, do we need to cover those? We talked about those earlier, right?
Yes, actually do. I don't know.
Well, Hunter thinks we should cover them. All right, let's do just the first one. I'm gonna do the X and Y intercepts for this one, but not the other one. So to find the X intercepts, we would set the equation equal to 0 and solve for X to find the X intercepts. Notice I don't know where it crosses the graph just by looking at the graph. I have no idea. But we can solve for x. We can add 1 to both sides. We get 1/2 times the cubed root of x minus 4 equals 1. In order to undo the 1/2, you can divide by 1/2, or I would recommend multiplying by the reciprocal. That way you don't make any mistakes trying to divide fractions. 1 times 2 is just 2. 1 times 2 is just 2. How are we going to cancel out the cube roots on the left? We're going to raise it to the third power. So we get x minus 4 equals 8. 2 to the third is 8. And then we can add 4 to both sides. Plus 4 to both sides. And we get x equals 12 for the x-intercept. X equals 12. How do we find the y-intercept? The y-intercept is actually the easier one. We're just going to type it in the calculator. Y equals 1/2 times the cube root of 0 minus 4 minus 1. We're just going to plug 0 in for x for the y-intercept. Always. It doesn't matter what function we have. If we have square root, cube root, exponential, logarithm, quadratic, we're going to do rational functions in a couple weeks after spring break. It doesn't matter. If you find the y-intercept, plug in 0 for x. How do you type this in your calculator? You want to hit the 1/2 button. You want to hit the multiplication symbol. You're going to type the number 3. And then you're going to hit this button that looks like this. It looks like the square root, but there's like an X indicating the root. And what's going to happen in your calculator is that X is going to become the 3, right? It's going to take that 3 and it's going to put it where the X is. If you wanted something like 2, let's say it was 2 times 3, and you typed in 2, 3 without a multiplication symbol, and then you hit this button, guess what number it's going to put inside the root?
23.
23. We don't want 23 there. We just wanted the 3 there. So you do 2 times, and then it's only going to put the 3 there. But if you don't actually write the multiplication symbol, with the fraction, it might be a little bit different with the fraction. You may not need the multiplication symbol for the fraction. But if it's not a fraction, you definitely need the multiplication symbol. And you get negative 1.79 if you do type that in the calculator. Don't ask me how I remember that for the first period. Maybe, yes, because parentheses means multiplication, so I think that would be okay. All right, last graph today. I'm gonna skip the x and y intercepts for this one. The +2 is gonna move us to the left 2. The -4 is gonna move us down 4. So that's the first point that I'm gonna put on my graph. Left 2, down 4, starting at the origin. Left 2, down 4. That point is not affected by our stretch, our shrink, or our reflection. It does not matter if there's a -2 in front or any number in front for that matter. You can change that number to any number you want to change it to. And that point, -2, -4, is still going to be on your graph. That's the only point that would be on our graph if we change that -2 in front to any other number. Is that point. So now how do we graph this? This is a -2, so if we talk about reflections, it does reflect over x-axis. And then the 2 is going to be a stretch. I'm going to get lazy for a second, just do stretch by 2, technically by a factor of 2, but that's okay. So in this case, if this were a square root function, the right side would go down. Well, a cube root function, guess what? The right side also goes down. So the stretch, we're stretching this point that would have been right here, I guess. We're reflecting that point and stretching it. So that point ends up being 2 below that center key point that we've talked about. And then we can sketch the right side. Kind of look like a parabola again, going to the right. And then the left side, since the right side went down, the left side's got to do the opposite. So the left side is going to go up 2 on the back side. It's going to look something like that. If all else fails, what can you use your calculator for? You can make a table in your calculator. And once you make that table in your calculator, every single point that I've put on the graph today would have showed up in your table. This point right here would have been in your table. This point right here would have been in your table. There might be some other whole number points also in your table. You can also plot the decimals if you need to. What is the domain and range for any odd roots, no matter the transformations? Negative infinity to infinity. Always, always, always. And the end behavior. The end behavior is gonna be a little bit different this time because we did have a reflection. And that reflection, the left side is no longer going down. The left side is actually going up this time. And the right side is going down. So the left side over here is going up to infinity. So my first statement, which is talking about the left side of the graph, is going up to infinity. And my second statement, which is talking about the right side, and the right side is going down to negative infinity.